So then the usually last step is to do the routing, which is again automated. So what does routing do? It connects all these cells. So all the cells, the standard cells which were placed were not connected to each other, so they're now connected with interconnects, so wires. And it usually finds the best possible connection between the cells to start from the source to the destination. So there are several important points to note here. One is it has to meet the timing. So usually you would have specified some constraints in the STC, which was provided as an input to the place and route tool, and the tool that we use is Cadence Innovus. I must have mentioned it earlier. So it usually does routing such that it meets the timing. There are also several guidelines as to how the routings has to be done. So usually the wire never bends like 90 degrees. So usually avoid wire bends because the signal quality is lost when you actually do such orthogonal bends. So wire bends are usually avoided. So that also means that L-shaped wires or any other these kind of bends are avoided. You usually never do zigzag kind of wires. So Z kind of wires are usually not done. So there are several um, routing guidelines. In addition to just these, there are several other guidelines such as the width of the wire, the spacing between the wires, and what is the amount of crosstalk it would induce on each other. So all of this is part of what is called signal integrity. So to maintain the quality of the signal from the source to the destination. So usually there will be losses. So there is it's expected that the signal goes through several losses along the path to the destination. But at the destination or at the receiver, you usually have certain specifications to meet. So for example, if you sent a 1.2 volt signal, you don't really expect the same here. So you would probably have a different set of specifications here to identify it as a high and a low. So you have to meet that specification. So that is very that's also technology dependent. It's also dependent on the interface. So for example, DDR might have a different specification from PCI Express, for example, or there are other signals like DisplayPort, HDMI, USB. So each of them have a different specification to be met, and accordingly, these routing guidelines are usually specified. So how does the router in this tool do the routing? So there are several algorithms, but one of them is shown here. It's called the maze routing. So what happens is you start with the source. So if this is the source, I'm just going to highlight it here. The one here is the source, and let's say this is the destination. The one that I'm showing here is the destination. So this is the source and this is the destination. So around the source, you start with the number, you start with numbering it with 1. So you put a 1 here and surround it by all the 2's. So I'll just write it here. So you surround it by 2's and then surround that by 3's and so on. And so on you go till you hit the destination. And once the destination is hit, what you do is you just find the path from the source to the destination along some path which usually has the 1, 2, 3, 4, etc. up to 9. So you're going to follow this numbering along a certain path from the source up to the destination. So whichever path is that is going to be the path for the route. So this is just one of the ways, but there is a lot of memory used here. So you'll see that there's a lot of memory wasted here because you're saving so much of information here which is not really useful. So it may not really be the best way to do, it may not be the best algorithm in terms of time and memory and so on. But this is just one of the ways. There could be several other ways in which the router does the routing. So this is how the layout will look like after the routing is done. So all of these wires shown here are all uh, routed. So this is usually the last step, and we're mostly done with this. Then finally what you do is do a design rule check. So again, the technology or the PDK would have specified certain design rules, and the tool will verify the design with the design tools. So some of the examples are wire width separation, like I mentioned before. The width of the metal, is there a short or are they crossing each other? And are the vias connected? Is the via dimensions correct? Spacings. So all of these are usually checked. And if it violates the DRC, it will also specify where it is violated and you can go and fix it. So usually, if you do manual routing, you might have issues with DRC. If you have done it automatically, typically you should be able to get a DRC. You should get a DRC clean, which means that there are no DRC violations. So finally, what we do is extract the parasitics. So what are the parasitics? So usually you will have, if you have a wire, you'll have to model it somehow because this is going to have some delay. So if you have sent a signal from this point to this point, it is not going to come at exactly the same time, and it is not going to come with exactly the same quality. So you might have overshoots, undershoots, and loss of signal quality, loss of edge rate, and so on. That is because it is going through a path, and especially if it is a high frequency signal, it is definitely going to have certain effects, which we will discuss later if time permits, called as signal integrity issues. So you'll have to model this wire somehow, and the longer the wire, the more other effects going to be of these issues. So typically it is modeled with uh, resistance, inductance, conductance, and capacitance. It's called an RLGC model. You could also just model it with an LC model or just an RC model. It depends upon depends upon the frequency of the wire, the length of the wire, and the dimensions of the wire, and so on. So that is what we call as parasitic. So parasitic capacitance, it could be inductance. So it could be any of these components or all of these components. So typically we extract it from the layout that we have just created. So we've created a layout. That's what we saw in the last slide here. And from this, we are going to extract the parasitics of all of these wires. And there are two formats. This is the SPEF and this is the DSPF format. The DSPF is more readily convertible into SPICE format for simulation. So I usually prefer this format. So once you get this, this is nothing but a SPICE version of the same RTL. So for example, if you gave a counter, for example, you will get a SPICE netlist for the counter, which you can actually test with certain inputs. So you can simulate it with some test inputs, and the same test inputs given to RTL should give the same output. So that's how you know that the layout is correct. So if the layout is correct, then the extracted SPICE netlist should behave functionally the same way as the original RTL behaved. So if that works, then that means that the layout is perfect. Of course, you'll also have to, you will have several parasitics there, but then once you simulate it and functionally verify it, you also verify the timing, etc. So then that means that the layout has been correctly generated. So as a last step, you can actually stream out GDS. So GDS is the format which the fab or the manufacturing unit will use to actually fabricate the chip. So you can extract or stream out GDS as a last step and provide it to the foundry to manufacture it. This is usually called the tape out. So you stream out the GDS and tape it out to the foundry. There are also other steps like timing, sign off, etc. This would be done as part of the static timing analysis to make sure that the timing is met. So that is the last slide we have here. So this is a brief about how we go from RTN to GDS.